I guess if you chose like a very large number, maybe even I don't know, like 100 seconds, you could have a larger percentage of being off.
It shouldn't be. I think if you picked a number,
I mean, if we're off by half a second at 0.005 seconds, would we be off by like a handful of volts by that point?
it shouldn't matter, shouldn't.
Ideally.
Intellectually, it should not matter. Again, emotional scars. I don't know what my parents did to me to make me feel this way, but they did something.
Yeah.
All right. The lab that you're gonna do on Thursday is an RC circuit. The numbers will be different. So, the trick in when you're doing the measurements, with DC, there's a high potential side and a low potential side. And so, you know which way the current's gonna flow. But with alternating current, at least if you're using the older machines, they're both red. It's not a black and a red there. They're both the same color. And so, which is the high side, which is the low side? Well, it flips back and forth. And so, the way you work it is you make an assumption. You go, I'm going to assume that this is the high side in terms of plotting out how to put my probes. So you pick a side to be high side and a low side, you pretend the current's gonna flow that way, and then when you set up your current, you put in the current probe, current sensor, whichever one it is, the current meter, from the lab quest, you make sure that it is set up so that the current's flowing in that direction. Voltage, this is the high side, that's the low side of voltage, so you set up your the differential voltage probe accordingly.
Do we will we ever get to like something like a mesh analysis with the AC circuits?
I don't do that yet. Because usually by the time students get to here, I've had classes of 20 where there've been 2 people who've done something similar to that already, and no one else has. And the physics approach is generally phasors. I will get into, for the first time, I'll get into the complex number analysis, which would go along with the mesh analysis if we go that far. Anyone else done the complex number analysis for AC circuits? I assume you've done it, or you've seen it?
I've seen it.
Okay. Okay. We'll leave that there, let's get rid of this. Let's do an RLC series circuit. Now I did the order of resistance, inductor, resistor, inductor, capacitor. It doesn't have to be in that order, just so long as they're in series. As with any of these, the first thing to start out with is there anything common to everything?
Current.
So let's set up our phasor diagram. We start out with current. Now I'm going to do it a little bit differently because typically I started out in the first quadrant. I'm just going to start out with my current straight up on the x-axis here. Oh, I'm sorry, on the horizontal axis. And there's my current, which is the current for the power supply, current for the inductor, current for the capacitor, current for the resistor. This one. So I got 4 phasors sitting right there, all on top of each other. Next step, we apply the ice band. And I know resistance isn't part of Eli the Iceman, but what is the direction of the voltage phasor for the resistor?
The same as the current for the,
Yes, it is. All right, now we bring in the Eli and ice. What is let's Eli start with him. For the inductor, which way is the voltage for the inductor pointing?
before. Or
So
90
it'd be
degrees.
90 degrees.
It's 90 degrees, okay, I'll agree with that.
Up,
Why up?
because it's before the current.
Yeah. Now remember this, in this, the memory trick here, E stands for EMF, so it's voltage. So for an inductor, voltage comes before the current, so it is up. And for the capacitor, which way is the voltage phasor for the capacitor pointing?
Downward 90 degrees.
Now, I don't know which one is bigger right now, VL or VC. I just arbitrarily pick one. It'll come out in the end if we need numbers here. Now, in order to find, again, if I'm going from here to here, the voltage across my power supply should equal the voltage, the sum of the voltages across the other three. So I'm gonna add my other three phasors, my other three voltage phasors, in order to figure out what the voltage for the power supply is. And somewhere I've got a color that might stand out. I'm going to just assume VL is bigger than VC. They're in opposite directions, we add them like vectors. And so I'm going to assume that the sum of these two is something that's pointing upwards. And this is VL minus VC. Or VL plus negative VC. I guess technically VL plus VC, but it's pointing in that direction. It's a small little nub there. And then when I add VR onto it, I get the voltage phasor for the power supply. I know that epsilon sub naught squared is equal to VR squared plus VL minus VC squared. It's Pythagorean theorem. Now I bring in that stuff. This is I squared times the I power supply times Z squared is equal to, I guess all my I's are the same, but IR times resistance squared plus I times X sub L minus I times X sub C squared. I can factor an I out, all my I's are the same, I can get rid of them, so what I'm left with is Z squared is equal to R squared plus XL minus XC squared. Taking it that last step, because we have a formula for XL and XC, Z is equal to the square root of R squared plus omega L minus 1 over omega C squared. And there's the formula for the impedance for the RLC series circuit. That is the formula that shows up in the summary section under special case. It's very similar to the one we did for the first one where I didn't have an inductor. So if the inductance was 0, that term just drops out, and I'm squaring a negative, which makes it positive. We end up with what we had before. And then we can go through some of the similar stuff we did before. I was gonna stop it there with just, this is the formula for the inductance of the RLC series circuit. We'll do the inductance for the RLC parallel circuit, and then we'll get into more complicated finding the impedance. And then we'll get into more complicated and actually use numbers. That's the plan. Any questions to hear? All right, what's the first question? Or the answer to the first question?
Voltage is the same across.
So that's what we start out with. So that's my power supply, plus across the resistor, plus across the inductor, plus across the capacitor. So we've got four of my phasors right there. All I'm missing are my current phasors. So let's bring it back, Eli. Where does one of my current phasors go? Hint, we need to do power supply last.
The resistance goes right on top of that.
Yep. All right. That's IR. So that leaves current phasor for the inductor and for the capacitor. Let me just write it up here.
For the conductor, it's 90 degrees down.
So for the inductor,
For the conduct.
EMF, the voltage comes before, so.
For the capacitor, that's what I was thinking.
Oh, you said capacitor?
Yeah, thought.
For capacitor, current comes first. Again, these things are spinning around like that, so current would be up 90 degrees. Then inductor, now, I made IC longer than IL. I don't know if that's actually true or not. It doesn't matter. If it's wrong, then what I'm squaring is the negative, but it gets squared, so that the differences get washed away. For the power supply, I know that the current coming out of the power supply gets split among the other three branches there, and so the current across each of these, if you add them up, should add up to the current across the power supply. So I'm gonna add up my three phasors there, and you add them like vectors. I'm gonna start out adding these two together. Then I'm just gonna label that IC minus IL. And then, wow, that was a whole lot similar to what I just did. And that would be the current for the power supply. So I set up basically, the length of IPS there is based upon the Pythagorean theorem. So current coming out of the power supply squared is equal to IR squared plus IC minus IL squared. definitely need to make sure my L's and C's don't look like the same thing. See how this one does. Now I know voltage is the same, so it'd be nice if we work voltage into it, so let's do it. We have these Ohm's law analogs over here. So this is the EMF over the impedance squared is equal to the voltage across the resistance, voltage across the resistor, resistance squared plus VL over XL minus VC over XC squared. Again, all my voltages are equal. I can factor those out. They go away.
So IC is equal to VL over XL? Or is it?
IC is this and IL is that. I missed the full question, sorry.
So did the L's and C's swap?
Oh,
Okay.
thank you.
I was just trying to understand.
Now, fortunately, if this were a test and I did something like that, because I'm squaring it, the problem would
Yeah.
go away, but yeah, you're right, that,
I'm just trying to understand as we go along.
yep, nope, appreciate that.
When we did Eli the Iceman, is the epsilon being converted to an E for that?
Yeah, pretty much.
Okay.
Yep.
I couldn't remember what E stood for some reason. Okay.
E for voltage, come on.
Yeah. And for everything else.
So I'm left with 1 over Z squared equals 1 over R squared plus 1 over XC minus 1 over XL squared. And so I have a formula for impedance for the series, for the parallel circuit. Z, my impedance, is equal to 1 over the square root of 1 over R squared plus omega C minus 1 over omega L. So we have a different impedance formula, which is going to be true for any time we have a new tech circuit.
And omega is angular frequency.
Yes. As determined by power supply. Questions to hear?
What do you do to find omega again?
In the previous problem, I gave you the frequency of the oscillation. So for instance, frequency is, in the US, the frequency of our power supply is 60 hertz.
Okay.
The angular frequency is 2 pi times the frequency.
Okay.
So I think Europe and is 50 hertz.
Yeah. So typically that'd be something quasi-given.
Yeah. Yeah. Just like the value of, this is usually quasi-given. Like in the last case, I gave you the RMS value, and this is the peak value, so just multiply times square root of 2. Other questions? All right. There you go. I'm going to do this, solve the next problem 2 different ways. On picturing solving it using the Phasor diagrams, and then we'll do the complex number analysis. And then you figure out which one you find easier. I also warn you that right near the end, there's a small little mistake that I know is gonna be there, unless you catch it right after I make the mistake. Because there's another piece that you need to make sure you're thinking about. And honestly, it's the mistake that I made, that I spent way too long trying to figure out where my mistake was, and then I had a dull moment and figured out what my mistake was. All right. So we have RL parallel to C circuit here. Some values. My resistance is 15 ohms. My inductor is 45 millihenries. My capacitance is 200 microfarads. RMS voltage of the power supply was 120 volts. Let's stick with a frequency of 60 hertz. And anything else I need to give you? And we'll just establish that the phase shift of the power supply, 0. So we're establishing our basis right there. Now, given a problem like this, there's not one thing that's common to everything. There's something common to this line, the RL combined, and something combined for C, and something for the power supply, but what do you start with? RL have the same current, or the resistor and the inductor have the same current, but the voltage across